Okay, hello again. This is the second video for the first part of chapter 20 on magnetism. So this time we're going to be using what we discovered about when wires are interacting in terms of the forces that they create on each other. So this one says we have two current carrying wires. They're in an appliance. You can think of this appliance. Looks like it says DC current. So what kind of appliance might this be? Something with a battery? Maybe a flashlight or something like that. I don't know. Any kind of battery operated appliance would be DC, but pretty much. Anyway, it says we have two wires inside that appliance. They're 3 millimeters apart, so really short distance between them. That makes sense, right? Inside the handle of something or something like that. It says there's 8 amps in them. They are 2 meters long, so maybe they're like wrapped and they go back and forth and stuff. I don't know, because 2 meters is a long way. It says calculate the force that one wire exerts on the other. So if you remember last time, we kind of derived that. So we started by looking at this expression, which talked about the force due to a wire of length L, and then we had the B field of a very long wire, radius R away from that. And if you remember, we kind of combined those two in these other examples, and eventually came up with this expression right here. So it's got the currents multiplied by mu naught over 2 pi times the distance between the two wires, and you've also got like the length of the wire in there. Okay, so let's go back and apply that formula. Where am I at here? Nope, that's the one we're going to do next. Here we go. So we have wires that are 3 millimeters apart, and we want to calculate the force that one is producing on the other. I guess they both have that 8 amps, so we'll like have 8 amps squared. So the force is going to be mu naught over 2 pi. So that's going to be 4 pi times 10 to the negative 7th. I guess we could simplify that, right? And just say 2 to the negative 7th, but I'm not going to. I'm just going to say this. Just follow the formula over 2 pi times the radius between them, which we said was 3 millimeters, so 3 times 10 to the negative third. There we go, it's not squared, right? Just 2 pi r. And then we had both currents, so the current through both wires is the same since they're both in this device. I guess, I don't know what kind of circuit they're in, but we'll just say that it's the same through both. So maybe they're like in a parallel circuit or something. So there's 8 and 8, or you could just write 8 squared. And then what else? Didn't we have to figure out the length of the wire? So times the length of just one of the wires. Since they're both the same pretty much in this case, it really doesn't matter. So we can stick that in our calculator and we'll have our answer. So it should be in Newton since it's a force. So I think that is the force that they are exerting on each other. We don't really know the direction of that force without knowing the direction of the currents, so that would depend. Okay, let's do one more example. All right, so this time, let's see. Suspending something. Cool. I think this one has a current that is a fixed distance away from another wire, and we want to figure out how much current we need to run in that second wire for it to like levitate. So you can definitely do like levitation with this kind of stuff. So that's pretty cool. So we're going to say we want it to be 20 centimeters down. We know that we have to put 80 amps in this wire up here that's going this way. So we're flowing that one this way. And we want to know how much can we run down here to make it levitated according to gravity. So we are going to factor gravity in here. That's pretty neat. And it says the lower wire has this fixed mass of 0.12 grams per meter of how long it is. So, of course, if it's longer, it weighs more. All right, so first I think we should just calculate gravity. So we have a little free body diagram. We're going to have the magnetic force. If we want it to levitate, we better make that go up. So think about it. This guy, since it's going that way, is going to if we want it to come up like this, then we need the wires from what we just learned to be running in the same direction if we want that repulsive force. I mean, excuse me, attractive force, right? So if we want that to be coming up toward the other wire, we better make sure this guy runs that way. So that's part of our question. That's the direction we need to flow the current. Now, how much do we need to flow in there? That's the other question. So, okay, free body diagram, we've got this force coming up, gravity coming down. So what is gravity? It's that 0.12 mass. And then notice we can get the meters to cancel here by just doing it for 1 meter at a time. So that's what we'll do. Times 9.8, so that's how much force gravity is trying to pull down on the wire with. So we just need to balance that. So we say, okay, here's our expression that we've been using now, right? For the force between the two wires due to their magnetic interaction. And so we say, okay, we have 80 amps in the first one, so we can put that right here. U naught and 2 pi are just constants. L was, did they tell us about anything about how long they wanted? Oh yeah, remember we made this part 1 so that we could figure out, since it said 0.21 grams per meter. I guess we could have said 2 and then put a 2 right here and doubled it. That was kind of our choice, so we're going to put that in for L. Okay, and then we're going to solve for I2. D, we said we wanted it to be 20, so 0.2 on that one. So then you just solve for I2, and you get that you need to run 15 amps in the same direction in order for that wire to levitate. Crazy, right? I really like that one. That's pretty neat. Okay, I hope you found this useful. I'll see you in class Monday.